Okay, let us begin then. So, this class is going to be basically a repeat of one of the other classes we've hosted in class 3 before, as we're continuing on with the kinematics side of stuff. Position,
Yeah.
velocity, acceleration, that sort of thing. And so because we've done it before, I'll keep it fairly brief as far as the overall lecture portion of it. The overall plan was to do it as sort of a uh, fielding questions from the group and going through the questions, or at least the key ones in the chapter and the review section. Although we'll see how turnout ends up being. If you tend to be the only one in the class, then we'll do a class based on whatever you're currently up to. How's that sound?
Yeah. Oh, sweet.
Cool. Okay, position and average velocity. So position is pretty much something we've been talking about for quite a while now. Position is simply the distance between some starting point and some ending point. And so the thing that's the most confusing about this area of study is going to be the fact that they both use the same word known as origin. Right? In the sense that the origin on an XY axis would be this point here, but the origin is also used to refer to the reference point from which we are observing the location of a particle. Like for instance, yes, this is the origin on the graph, but when you're over here on the graph, this is considered roughly, we'll call it like, I don't know, maybe 9. It's a bit below that 10. 9 units away from the origin. You don't just draw a straight line connecting those 2 points and measure the distance. No, x is position away from origin. And so effectively, this and this all over here are the exact same spot in physical space. They are both the same distance away from the origin, that being exactly over the origin. That's why the main thing that gets confusing about this, using the same terminology. But okay, that's as long as you've got your head around what's going on there, you'll be fine for the rest of it. Average velocity. So velocity is a vector. It has both direction and magnitude, which is why we use position for its equation, because position can be both positive and negative, where positive is to the right of the origin and negative is to the left of the origin. And
Chris, just a question. Can change in position just be like referred to displacement as well? Or change in
changing,
displacement?
well, yeah, displacement, change in position. Displacement pretty much is another word for position. They're synonymous. And so, yeah, I'm trying to think of a way you could phrase change in position as change in displacement. Um, I don't think yeah, I guess they're not quite the same thing because displacement basically implies you've started at some location, you've ended at some new location. I think,
Like distance from the origin?
say again.
And does that mean that position is like only from the origin?
Yeah, I think that's what I was going to get at, which is position, I believe, is purely with reference from the origin, whereas displacement can technically have a variable start location. So
Okay.
if you started 3 meters away from your origin, your displacement from that starting point and where you end up isn't necessarily going to match the position away from the origin. Yeah,
Okay.
it's an interesting thing to bring up there. That's my interpretation of it. I haven't got that like bulletproof yet, so you'd probably want to double check that. But that's what seems to be the case from my understanding of it right now.
Yeah, cool.
Good question. Yeah, nice. But okay, the key thing to understand when calculating stuff with velocity, you're using positional information. Whether you're doing average velocity or instantaneous velocity, technically, both of those are still using positional information. One being the rise of a run, so change in position, the other being the derivative of position, both of which are using positional information. Um, the only one that looks at here, well, this is pre-derivative stuff, so you'll typically not be required to do the derivative of your position equation. Although yeah, you do get some velocity graphs and velocity equations. Are they going to give us any velocity equations? Instantaneous. Yeah, okay. They play with it for a bit. They don't give you anything like concrete. They kind of just get you to analyze the overall slope. Is it positive? Is it negative? That sort of thing. Um, yeah, the other thing you'll have to be able to interpret are your velocity time graphs. So they call it velocity time and then they show a position time. Nice. Okay, so I guess the intention here is to start with your position time graph and then create your velocity time graph. We've kind of already seen this. Velocity is always the slope of position. So if you have straight lines in your position graph, one of the easiest things you can do is literally calculate the slope of each of those sections, and then those become the constant velocities of your actual velocity graph. Now, because you've got these sharp edges, this instantaneous change in direction, those are going to come with open circles on your velocity graph because it's impossible to tell what the actual velocity is at that spot, whether it belonged to the 10 kilometers per hour or the negative 15 kilometers per hour. That's also true of when you're doing your derivative graphs from original, right? Anytime you have sharp edges, you're non-differentiable at that spot. If you have anything more complicated than a straight line, you're going to either need an equation that describes that line before you can give any velocity information, right? This is through derivative and stuff like that. Or you're going to have to be a bit more ambiguous with your wording. Like for instance, if this was concave up, kind of like a positive parabola, you would say it's accelerating because the slope is getting steeper over time, but you wouldn't be able to give a specific number to that necessarily. Again, this being pre-derivative, you're not going to have that. They do keep it fairly chill in the sense that it's pretty much entirely going to be straight lines, or if there are curves, they're not going to get you to... It was kind of like this other question we briefly saw here, where is velocity positive? Well, positive slope, positive velocity, negative slope, negative velocity. It's going to be very higher level, very generalized in the question style. I think that's another example of it here. So average velocity, just using your two position values divided by the run. And then, what is the instantaneous velocity at t? Oh, they did give a velocity equation. Cool. So where you have a velocity equation, that's when you're typically using your instantaneous, kind of like with slope. All right, what's the instantaneous rate of change? Well, you would go derivative, whether by first principles or by the easier way, using the lookup table. So yeah, those are the main things that are brought up here. A bit of stuff on position, which is more revision. Some more stuff on velocity, which is technically the first time in the chapter where they introduce it. And yeah, the differences between average and instantaneous velocity. Do we have anything to clarify there? Cool. Okay. So what I'll do is I'll drop the doc in the chat just so you can follow along with your own version of the book rather than having to wait for me to scroll up to things. We are going to do most of these live together. And so that's the idea. We'll do all the key questions of 16E, and then once I feel like we've run out of those, and if we have time, I'll then jump over to the extended responses, which, to be honest, kind of look very similar. How many extended responses do we have? Yeah, okay. Anyway, we'll do some key stuff from here first, starting with just some of the basics. So question 1. We've got a position equation, S of t. We know because it's told to us, the position function. We're told the units, t being seconds, s being meters. Find average velocity over that time interval, 0 to 1. What kinds of things would we be expecting to do? This will be a fully tech active thing, by the way.
Do we sub the points into the equation and then divide it by the run?
Yeah, precisely. Yeah, we're basically just doing a rise over run, pretty much. Cool. Yep. Average velocity is your average anything pretty much is always going to be rise over run of that particular thing. So if we define our function, just quickly speed through that. function is equal to 6x minus 2x cubed. Then we do our right over run. So h of 1 minus h of 0 over 1 minus 0. We get the answer of 4. That is not the final answer. What is the final answer? What's the most correct way of presenting that?
Is it 4 meters per second?
Meters per second, correct. Yeah. We're doing application style stuff. We do want to make sure we're including units in that. I might stuff that up, so someone can call me out if I forget to put a unit on anything. Part B is sort of leading you into the diff by first principles kind of approach. The whole idea of what happens when you shrink that interval. You'll notice you'll get a value that's getting closer and closer to that instantaneous rate of change. Fundamentally, you're not doing anything different in that question, of course, but it's more so the idea behind why they're getting you to do it. Okay, cool. Question 2, very similar thing. We may or may not do the actual calculations for it, although they do seem to be chill. 2a, obviously we've got a picture instead of a graph, instead of a function. What would we now be looking at doing if we're just saying, like, for instance, 2ai?
We'd be dividing the kilometers by hours
Kilometers by hours? Yeah.
of the
Yeah.
interval. Like for the first interval, we have the train travels 60 kilometers
Mhm.
and over 2 hours, and then the velocity would be 30 kilometers per hour.
Correct. Yeah. That's a nice and chill one. To put a bit more nuance behind it, when you do get to, like, for instance, between 2 to 5, how do you got to modify your approach?
So you want to look at the kilometers achieved at 5 hours and then subtract it from where they started at. So
Mm.
80 minus 60 over 3.
Yeah, correct. So again, it's the exact same thing of rise over run, but this time through the graph rather than through the function. Yep, cool. What's a bit more challenging is describe the train journey. So before we try to dive into a full description, what kinds of things would you want to be talking about? Like, what things would you start bringing up?
The direction of travel relative to the origin,
Sounds good to me. Yep.
speed,
Yep.
and like the time.
Yep. So we're talking speed, direction of travel, time. Probably one more thing that you might want to throw in there at some point.
Is it like when it returns to the origin but then continues to travel past in the negative direction?
Yeah, yeah. So you could mention the fact that it's doing a return journey. It's going away and then back. The thing I was specifically thinking of would be a bit of positional information, not just the direction it's going in, but like how far it ends up. Like I don't know, for instance, for 0 to 2, you could say the train travels a total of 60 kilometers over a period of 2 hours, right of the origin, which I guess we would have to call door of ticket office at Jimbara station, but God knows no one's writing all of that. Imagine writing that in the sack. 60 kilometers for a total of 2 hours at a speed of 30 kilometers, average speed of 30 kilometers per hour, as seen right of the door of the ticket office at Jimbara station. Okay, obviously that's excessive, but as long as you're hitting those key elements, and you don't necessarily need to hit all the key elements for every stage of the journey, as long as you're demonstrating that you can hit 2 to 3 of them on each section and sort of mix it up a bit. That way you can demonstrate broad understanding while also keeping things brief as you can. That will be a decent way to do it. Like, for instance, let's take a stab at doing the journey from 2 to 5. Who wants to try and describe that?
The train traveled to the train continued to travel away from the origin at 20 on 3 kilometers per hour for the time between 2 and 5 hours.
Yeah, yeah, that works. Cool. One of the things you can do is also talk about it like relative to the previous journey. Like you could say the train then slowed down to a speed of whatever, and then go from there. Not saying what you did was wrong, of course. I'm just giving you more things in the toolbox to pull from. And then for that last bit, I'll take either from 5 to 7 or 5 all the way to 8. Depends on how you want to word it. Who's going to take a stab at that one?
The train then returned to its origin
Mm-hmm.
uh in 2 hours at a speed of 30 kil 30 kilometers per hour. I don't think we need to put negative because I already specified it's returning to
Yeah.
its origin.
In fact,
And
if
then
you did include a negative, you would
that'll be the
actually
other
be a
way.
bit off. Yeah.
Yeah.
Because when you say direction, then you would almost, yeah, pretty much anytime you specify direction in your language, you don't want to put a negative on it because then you're going to reverse the direction. Um,
Yeah. And the slope looks like it's straight, but I think it's gone at 40 for the next hour.
uh, oh yeah, yeah,
But
yeah.
yeah.
It looks to be pretty constant there.
But yeah, sure, we'll say for the sake of it. Then continue to travel away from its origin
Mhm.
at 40 kilometers per hour for the next hour.
Yeah, that'll do. Nice. Drawing the actual velocity time graphs, sure, it's probably worth doing one of those. Um, yeah. Okay. Assuming we know the numbers of all of these, what would we start doing for like a velocity time graph?
From 0 to 2, we draw a straight line at 30
Yep.
kilometers per hour.
Yep, that's it. So straight line like that, 0 to 2. Horizontal, of course, because it's constant velocity. Constant slope means constant velocity, and because velocity is on our y-axis, it's a horizontal. That's good. Next journey, 2 to 5. What are we looking at?
Chris, I forgot to mention, but also the open circles at the end,
Mm,
because
yeah, that's good. Yeah, I was going to mention it at the very end if no one else did, to see if we could fix it up, but you've already got
and
there.
then from 2 to 5, we want to make another straight line, but like slightly a little bit below the first line because it's slower at 20 on 3 k's an hour.
Yep, that's good.
And then from 5 to 7, we want to make a line below the x-axis at negative 30.
Mm-hmm. 30. Now here's a question. Hmm. It doesn't say that it's stop. Does it? Hang on. What's the actual story? Following. Describe the train journey. Yeah, I guess you'd have to say it stops at at 8 hours. It seems intentional that it's stopping at 8 hours and not just continuing on forever. There's nothing else in the question to say whether or not it goes forever. Like the reason why I'm bringing this up at all is like whether or not you do this with your graph or not, or whether you just sort of chunk it off at the end. So for this one, I would still chop it off at the end, and still putting an open circle there for a slightly different reason. Why? This is going to test a lot of theory here, very obscure thing. The hint will be it's got to do with diff by first principles. Not allowed to be a dark circle. Why? Got to do with limit and if by first principles. How do we know if a limit exists? Anyone remember the criteria for whether limit exists or not? We say a limit exists if as approached from the right gets you the same spot as approached from the left. The problem with a graph that truncates like this is that you can't come from one of the directions. And so for that reason, technically, you can't do the limit here. And by definition, because derivative is a limit as h approaches, well, I buggered that one up, h approaches 0, you actually can't do the limit there. And for that reason, it's non-differentiable there. It's a very, very obscure thing, but that's why if you ever see it, you've got open circles at those spots on derivative graphs. Does that need any further explanation? I'd be surprised if it comes up, but maybe it might be like a one marker. Why is there an open circle at the end? Not sure. Anyway, question 3 is very similar, but you've got more. What are we actually trying to do? Draw the velocity graph, draw the position graph. We've kind of already done that sort of stuff, but we just got velocity and time information as opposed to position and time information. Let's go with question 4 stuff then. At what time is the instantaneous velocity 0? This one should be a quick fire, I would hope. We've done a lot of derivative stuff.
At 0 seconds and 5 seconds.
Instantaneous velocity. This is a position graph.
Oh, my bad.
Well, actually, sorry, you actually are right for one of those values, which is why actually I brought this up. Who did I bring this up with? I brought it up with someone, but this is actually a slightly wrong question. You're technically right by saying t equals 0 is an answer. The book isn't expecting that though. But anyway, where do you think the book's expecting an answer?
Is it the turning point?
Yeah, the turning point. So instantaneous velocity basically means derivative of position equals 0, which of course is going to be here. Now, this, oops, can't highlight that properly apparently. Really? Can I go backwards? Yeah, that's better. Starts at rest at origin. What does it mean if something starts at rest? What does that keyword mean?
It starts like stationary.
Yeah, stationary, which means 0 velocity. And so even though the graph clearly has a slope there, or at least certainly appears to, the book is only going to give or pay this as an answer because it was looking for derivative being 0. But technically, if you say something starts at rest, this should now also be an answer for instantaneous velocity being 0 because velocity, speed, no motion, no happening. That was a bit of an oversight though in the book. Shouldn't exist in a VCAR exam. Honestly, it depends on if your teacher's very physics inclined or not as to whether or not this may be an issue in a SAC. Can't really say for certainly, but Cambridge did it, so anyway. This one we kind of already talked about. Let's go with C. How far from the origin does the particle go to the right? Might have to eyeball it a bit.
6 meters.
Yeah, 6 meters. That'll do. Looks like it goes slightly above it, but close enough. How long does it take to return to the origin? We kind of talked about that one before a little bit, but let's just do it quickly anyway.
Is it 2.5 seconds?
To return to the origin,
Oh, my bad.
that's
5 seconds.
a yeah. I mean, that is an ambiguous question, isn't it? How long does it take to return to the origin? Um, doesn't necessarily say where it started, because if you yeah, I'm just sort of playing with words, I guess. I think the intention you definitely want to assume it starts at zero and then at time equals zero and then see how long it takes from there. But the fact that this was right before, I can see why you might have thought from there to there. That's fair. Yeah, I don't think they pay too much attention to these questions. Typically, when you've got like parts A, B, C, D, you don't look at what's happened before, or at least key introduction to the question don't pass over. The answers from these might help for the next question, but if they introduce something like here's new function or here's new whatever, it's typically self-contained within that subsection, whatever that letter is. This is a graph, but in terms of a table, and they really wanted to play with like proper scaling. Like for this one, they got you to literally use a proper ruler on your book and put everything to scale so that when you go and do your estimates of the velocity, you literally get out your ruler and you measure 2 points either side of where you wanted to go. Um, and you'd get much more accurate because you have a proper scale to work with. That's obviously a lot of work right now for the same overall concept, so I feel like I'll just leave that one for you guys to play around with if you would like to do something to scale as opposed to just being proportional for the most part. Okay, so we start getting into some of the more typical application style stuff. A stone is thrown vertically upwards, 10 meters above the ground is our starting point. Position time graph has been depicted where the origin is taken at ground level, directly below where the stone was thrown. The motion of the stone is in a straight line, or as close to it as possible, I suppose. Yeah, okay. From the graph, estimate the instantaneous. Of course. Yeah, okay, whatever. If you just talk about how you would estimate it, I think that matters a lot more than the actual value you get. How do we estimate the instantaneous velocity with which the stone is thrown? So instantaneous velocity being velocity at a specific time value. Obviously, we have a position graph, so we can't just read it directly off. If you were to try estimate it,
Chris, I know it's an estimation question, but is it possible that we can sort of figure out the equation of the graph by looking at it?
yeah, can we? You have the point 010, you have the point 115. You could assume it as a parabola.
Like a
Yeah,
negative parabola
yeah, you could
and
do that
shift it up and whatnot.
because you've got 2 points to work with, one of which being the turning point. So you've got your h and k values done. So you got what, x minus 1 plus 15. Um, then you just got to solve for a, which is going to come from subbing in this point. I guess you have to assume it's a parabola is the thing. Looks like it, um, but of course, yeah, the assumption is that it's a parabola. But yeah, if you were told it's parabolic, which yeah, it should be parabolic. Like real world, if you throw a stone, it's a parabola. Projectile motion does follow a parabolic arc. Yeah, yeah. If you had to, you would. But yeah, as stated before, this is an estimation. So going through that route, I mean, you still might get the answer right, but if you show that kind of working, you probably don't get a mark for working because you're trying to demonstrate a different approach to it. It's kind of like those questions which say solve using X or like solve using completing squares, solve using factorizing. If you use a different approach, you're going to not get the mark for working on that. So for
Would
estimate,
an estimation of 5 meters per second be all right?
probably. I was more hoping to hear a bit about your reasoning as to how you got there.
Uh, just by eyeballing, it looks like it's about like the position is 15 meters away from the origin
Yep.
at 1 second, and it starts at 10, so 5/1.
Yeah, that's solid. That's fine. Taking the two closest, most easily recognizable points seems appropriate. Another line of thinking could be, sure, you might sacrifice a little bit of accuracy by trying to use this zero point 0.5 value, but because it is closer to the starting location, the slope should technically or theoretically be a bit more in line, as long as you're able to estimate the y value good enough here. That's another line of thinking you could follow, both of which are fine. This is why these can't really be assessed in a SAC or exam, unless the only thing they're talking about is your reasoning behind the question. Um, I'd say those are probably the two more valid ways going about it. At what time does the stone reach maximum height? We talked about that already. At what time does the stone hit the ground? That one should be, well, you'd have to sort of estimate it, but it's there. And then from the graph, again, okay, so we've done instantaneous. Instantaneous speed versus instantaneous velocity. So we'll just briefly talk about what do you have to change. The overall approach is the same, with the exception of one thing, which is instantaneous velocity versus instantaneous speed. What's the key difference?
We remove the like because when it's gonna hit the ground, right? It's the velocity gonna be negative, so all we do is just remove the negative because speed is a scalar quantity.
That's it. Yeah, speed is always positive. Velocity can be positive or negative. Sweet. Okay, let's see if question 7 has anything unique in it. Again, it's a position graph. We've talked about origin stuff. For which values of t is the particle moving right? We've we've kind of talked about this, although the way this graph looks might make it a bit tougher to interpret. Let's try it. For which values of t is the particle moving to the right? I'll also use a bit of this background information to help. No, this is actually unique. We haven't talked about this yet. That's the only hint that I ought to give there without giving it fully away, what the difference is. I was about to say that wrong answer, actually. Oh no, he's crashed. All on you, Pia. No, he's back. Mm. All right, I'll try to reword the hint a little bit differently. Moving to the right is not necessarily the same as being to the right. Another hint.
Wait, sorry, I just uh disconnected from the call somehow. I
Mm.
missed what you said. Could you just repeat that?
Oh yeah. I don't think I said anything while you were gone because I did see the disconnect, but I'll repeat it anyway, which was the other hint that I'll give is moving to the right isn't necessarily the same as being to the right. That's why this is a bit different. We've looked at what happens to like be on the right hand side of something, but moving towards the right hand side is a little bit different.
Like, isn't it like so from where it starts, right? And negative 20,
Hmm.
and then all the until like t is somewhere between 2 and 3,
Hmm.
moving towards the right, and then also from approximately t is equal to 6 to onwards from that, because it doesn't really define whether the graph is stopping there at 8.
Yeah, yeah, that's fair. Yeah, basically, so moving towards the right just means you started at some position and your position values are increasing, right? So you've got some fixed location, for instance, if I go to the handwritten section now, you got your origin, fixed spot. The question tells us we start 20 meters left. So we start over here at negative 20. Moving to the right is fine. You can move from here to here and still have a negative overall position. You're still left of this spot, but your direction that you're moving in is going towards the right. And then just for completeness, why not? Where is the particle stationary? That one I believe we've looked at before, but let's try it anyway.
Is it turning points?
Turning points. Yeah, correct. Particle
And
stationary.
not 0 this time because it
Mm.
doesn't say it starts from rest.
Yeah, there's no keyword rest there, is there? Yeah, let's analyze this real quick just in case there's anything else I can poke at. Moving horizontal straight line, position, starts, left, position time. Yeah, that seems fairly bulletproof. Cool. That's those. Um, Probably the more challenging questions are going to be your external responses, so I feel like it'd be better to move on to those. Although to be fair, these looked fairly tame. We've kind of done that stuff before. Average, well, there's your average speed versus average velocity. So there's a couple of things you have to worry about when you're doing average of a speed or average distance, average speed, those sorts of things. They have another little thing to worry about beyond just being positive and negative. This one's not going to have it, but it's whenever you have turning points in the way of your interval. Um, that's when you have to essentially calculate in two separate locations because speed is using distances, whereas velocity is using positions. So, for instance, and we've seen this picture before, but I'll sort of quickly redraw it again. If we have a graph like this, and we're trying to do average speed slash velocity from start to, let's say this is 5, from there to there, position or average velocity, you just do the slope connecting those 2 points. But for average speed, you need distance. And for distance, you need to do it in two parts. Distance is from here to here, and then from there to there. So you get your two calculations of distance, add them up, and then divide by your length of 5. That's the only other thing to bring up there. Um, there wasn't going to be a great way to show that in question one because it was a. If you look at what the question one parabola is, it's just centered at the origin anyway. It's just that. So whether you do speed or velocity for that, it's like whatever. There's no turning points in the way of the path. Otherwise, yeah, that's fine. Question two would be interesting. It's almost fully application. No real like immediate values you can just chuck into a graph directly. We have a vending machine. Machine starts 1/4 full. No drinks are sold from 1 to 6. Machine is filled at 2. Sketch the graph to show how many cans. Hang on. Sketch a graph to show how the number of cans in the machine may vary from 6 a.m. till midnight. Huh. What? That's an interesting question. That's so up to interpretation. I don't really know what that's doing in kinematics, but I could probably just leave that. I thought that might be an interesting one, but no. It's just got nothing to do with kinematics. 2 points on a curve, find the gradient, join the points in terms of A and B. Yeah, how's that? What do we do for this kind of question, 3A? This is like way back in diff by first principles type stuff. Anyone remember what's going on here?
Chris, do we do still like b squared minus a squared over
Mhm.
b minus a?
Yeah, yeah, still going to be rise over run. You've got two separate points. Um, you're not going to be able to tell which one's ahead of the other. So as long as you're consistent with whichever way you go, in this case you've done the B minus the A's, that's totally fine. Y2 take Y1, X2 take X1. Absolutely. You'll get them in terms of A and B, of course, and then questions B and C are going to be fairly chill because you're literally just going to be subbing in those particular values for A and B. Noting, of course, the similarity in it. All right, they've got a gap of 1 here, and then they've got a gap of 0.01. Again, this is diff by first principles, or at least leading up into it. The very next chapter is diff by first principles. These look identical, but you've now got a graph to work with. A1, A2 are points on the graph, so here and here-ish, and they're converging onto P, essentially. 1.5 to 2.5, you've got a gap of 1. 1.9 to 2.1, you've got a gap of 0.2, and then, well, you can see the gap just gets smaller and smaller again. Here's a bit more of an application. It's question 5, have a read of what's going on there. The key thing to do would be part B on this one. You'll probably need to estimate it, by the way, even though it does say calculate.
In 1960, the population was about 225 million,
Sure, yeah.
and in 2000 it was about a little over 500 million, so about 525, I'll say.
Yeah, why not? And so with those numbers, you do what?
Um, we subtract the like population in 2000 from the population in 1960, and then divide it by 40.
Yeah, and the 40 came from.
2000 minus 1960.
That's it. Yeah. Rise, run. Once again. Average anything is always going to be a rise or a run type thing. At least if you've got a graph. We don't, in methods, we don't look at like average. Sorry, the weighted average. That's where you start doing stuff like the mean and probability. Those are technically a weighted average. Um, in the context of anything graphical, you're pretty much always doing just a flat rise of a run. That's that. Here's an interpretation thing. How many years would it take, roughly, to double the 2020 population based on what you're seeing? This is, again, interpretation. No real wrong answer here. So we've got 2020 population about here. How long is that going to take to double? So let's call it, just for argument's sake, we'll call it, so that's 0.95 billion, so 950 mil.
I would say about 20 years.
About 20 years. Yeah, that seems about right. What made you shrink the overall interval versus what we had before?
Well, 2030 looks to be around 1.3 billion.
Yep.
And so that's like already like multiplying 950 by like a half and
Mm.
then adding it on top of it.
Yeah, yeah.
That means another half to go, and in 2040 it'd probably be around
Mm.
double.
Yeah, yeah. Solid. Basically, yeah, as long as you're identifying that this is exponential growth, right, you would expect that each consecutive double, um, well, yeah, I mean, for exponential growth, if the base was 2, then technically speaking, every double takes the same duration of time. But this one, yeah, I mean that only really applies if the base is 2. In this case, it doesn't seem to be because we are experiencing a longer duration of time for things to double. Like for instance, from point 2 to point 4, you're looking at from 1950 to about 1990. So the growth rate's definitely different. Anyway, that's
Hard
that.
to be like objective about this because
Yeah,
the graphs sound great, and then like it's asking us to calculate, but there's really no way we can calculate because
yeah. This should be an estimate. Like they did it right here, estimate. This one, that shouldn't say calculate. Um, Same thing with this, right? The actual, like, this entire thing has just been rise or run from the get go. Like, let's not beat around the bush on that. So the reason why I'm doing these questions is to try and test the understanding more so than the actual calculation, because it's always just rise or run. Okay, draw the graph, gradient, secant. Yeah, okay, whatever. As long as you know how to draw exponentials, you should be fine with that, especially these kinds of exponentials. Yeah, well, not even. I've said this so many times, noticing the decrease in width between those values. That's this. Okay, difference of cubes, fine expression. Yeah, okay, so still rise of a run, but when you're expanding your top, I guess you're not expanding, you're factorizing from the b cubed minus a cubed. You're now factorizing that. Fair enough. We've seen those before. Here's another one that looks like it could be used for interpretation. Got a sketch of what happens when 3 swimmers compete in a 100-meter race. Vertical axis is distance traveled by the swimmer. Who wins the race? So you've got distance on y, time on the x. Who won the race?
is this swimmer B?
It is swimmer B. Yeah. Why is that?
They've got to 100 meters in the least amount of time, so they're the fastest.
That's it. Yeah, that's good. Who is in front at the 50-meter mark? So, who's in front there?
Swimmer A.
Yeah, swimmer A. Again, for the same logic. If you draw your vertical line, whoever reaches 50 in that first section, or whoever's got 50 from that vertical line first is the winner. What's this? What's the approximate distance separating first and third when the winner finishes? So what they're saying from here, separating first and third. What's the, hang on, approximate distance separating first and third when the winner finishes? Yeah, okay. The wording around that can be tough, so maybe I'll let you guys try to interpret that. What's that actually telling you to do? Forget calculating it, like, what does it actually tell you to do?
We need to see like what the distance is between swimmer A and now this is like where sorry swimmer B and I'm not really sure if you want to because swimmer C is third at the time
Mm.
when swimmer B wins, but overall swimmer A comes third, so I'm just gonna say swimmer A and
Yeah, that's probably the best way of going about it. Doing the vertical distance from red line to blue line from that
yeah,
spot.
and that's
Um,
about 25 meters, I'd say. So yeah.
sure, yeah. I mean, the number was whatever. It was more so like the interpretation of how you made that decision. Um, yeah. So the reason why you probably do that rather than going straight to C is because you don't really get awarded a position until you finish the race, and so the first and third place person only gets awarded those things at the very end. Approximate time difference between. Okay, that's even more ambiguous now. Approximate time difference between first and third place. There's only really one thing that you could do that's bulletproof for that, or at least there's probably only one way to interpret that, but technically you could do the time difference anywhere in the race based on that wording. But if you were to guess where they meant to take your time difference, what do you think they intended to happen? These questions are phrased in the weirdest way.
I guess just the difference between the finishing time of first place and third place. So
Yeah, that
from
seems
what
to be
I
the
can see, it's about 45 seconds, I think.
sure. Yeah, that works. We'll call this 60. We'll call this 100 or so, something like that. Maybe a little bit before 60. Either way, but yeah, main thing being doing the time difference between the finishes, um, because that's pretty much the only. If you're calculating time difference, you need a position to judge them by. Like for instance, if you judge them here, there's no time difference, whereas if you judge them here, there's a bit smaller time difference. And then obviously because these are two linear, the time difference is only going to increase over time between them for the same distance value. Average speeds, that's sort of whatever. Now you're going to run into a trouble with A as far as how you do average speed here. Um, yeah, the two main things you could do would be to start finish and that's it. So you did from 0 to 100 or so, and so that's your average. Or you could do it in two separate parts because it looks like there's fairly distinct sections of the journey. So you could do 0 to 30 and then 30 to 100, and that would give you a that's a more nuanced way of going about it because if you do end up doing it that way, you can't just add those two speeds together. you have to then proportionally add them. So for instance, 0 to 30 is only a portion of the journey. 30 to 100 is another portion of the journey. And so when you add those two things together, you've got to multiply them by the proportion of what those actually were. Like for instance, so from if the whole thing is 0 to 100, then 0 to 30 is 30%, and then 30 to 100 is going to be your 70%. So basically, whatever this speed is going to get a multiplier of 0.3 on it, and then you add that to whatever this speed comes out to be and multiply it by the 0.7. Obviously, like going way over the top for it, but just another technique you could technically use, if not in methods in the real world when you do have to start plotting these data and putting weights on them. Fair enough. That made enough sense. The fact you have to weight it if you do it in separate journeys. Sweet. Geez, almost made it to the end. Of course, and there's describe the race as if you were a commentator. I feel like we've already got a pretty good handle on what was going on there. The fact that the changes of positions, we kind of already discussed that. And then something that's got basically nothing to do with anything we've talked about. Let's see. F of x is a well-behaved function. Okay. Assume that for f, the average rate of change is m over ab. Find average rate of change of y for all of these differences. Now this is kind of cool. This will be one to finish on, actually, because this is the kind of thing that you will actually get in a multi. Or at least a similar thing I've seen before. A whole bunch of stuff like that. Because we're sort of low on time, I'll semi-walk through most of it. So we have some random function f. We know nothing about it other than the fact that the average rate of change, so rise over run, is m over some interval ab. So because we're not told any specifics of the relationship between a, b, and m, we can do whatever we want and still be fine. So you could put your a and your b like this. You could put your b over here and leave the a. It really doesn't matter. If they don't tell you where they are with relation to each other, then you should be able to put them wherever you like. Same thing with the fact that the slope is m. We're not told if m is positive or if m is negative. We're just told that it's m. So whether you draw it as having an average slope of being positive or negative is up to you. And so as long as you draw some function that has a positive slope or an average positive slope in that interval, you should be fine. That gives you at least something to work off of. Now, for f of x plus c, what does that do to a function plus c?
Depending on what c is, it'll translate up or down.
Yeah, vertical translation. So if you shift this graph up or down, should anything happen to the slope over this interval?
Wait, hold on.
Yeah, if I just
So
physically...
A to B,
Yeah.
yeah, it could like it, it could become a little bit like more, or it could become less, depending.
Not quite. So when you shift vertically up or down, nothing actually happens to slope. And the quick litmus test for that is derivative, right? If you d dx on the thing, and you got a plus c at the very end, what happens to that c?
It vanishes.
Yeah, it's gone. So any constants that are on your function, vertical translations are a constant on the function, disappears, and so that shouldn't have any impact on slope. So the answer for 9a is going to be m. I know we are running over time, so if you guys need to go somewhere, that's fine. I will be very brief on the next two. And so yeah, plus c is nothing. Part B, c times f of x, that's a dilation factor, so we're stretching along the y. And so because we are now stretching along the y, if you think about if you had derivative of regular f, you get f dash. If you have derivative of a f of x, you get a f dash because it's a constant multiplier. And so instead of the gradient being m, it's now a m over that interval. Exact same logic for c. If you've got a negative, so that's the same thing as having a as -1, basically. You now have negative f dash, and so you now have negative m. So all in all, if the graphing and imagining things moving is a bit tough, just think about what happens logistically when you do derivative, because that'll make it super clear. All right, any final questions, let me know. Otherwise, I'll let you enjoy the rest of your days.
Thank you, Chris.
No worries.